Today we're going to be looking at our learning target 3 from Unit 6, which is I can perform operations expressed in scientific notation. So we're going to focus today mostly on addition and subtraction of scientific notation, and there's two different ways that we go about this. Sometimes we'll have problems that have the same exponents, which we will be referring to as magnitudes, and then other times we will have problems where the exponents are different or they have different magnitudes, and we will have to adjust them to make them the same to be able to perform our addition and subtraction. So to find the sum or difference of numbers in scientific notation, the powers of 10 must be the same magnitude. So you have to have the same exponent in order to add or subtract scientific notation. So if you have problems that have the same magnitude, you're going to add or subtract the significant digits, whichever the problem is asking you to do. The power of 10 stays the same. And then if your solution is not in scientific notation after you add or subtract, then you need to convert it back into proper scientific notation or proper form. Looking at our first example, we have 7.78 times 10 to the 34th plus 5.35 times 10 to the 34th. So we should notice that our magnitudes are the same at 34. So we are going to add our significant digits. So 7.78 plus 5.35, and that gets us 13 and 13/100ths. And then the power of 10 stays the same. Now, looking at that, we should notice that 13 does not fall between 1 and 10, which means that I am going to need to move my decimal one place over so that I get 1.313. And if I'm swinging my decimal one place to the left, I need to add 1 to my exponent. So we have times 10 to the 35th. And that would be your solution to your original addition problem. In number 2, we have 9.62 times 10 to the 25th minus 2.58 times 10 to the 25th. And again, we have our magnitudes are the same, our exponents are the same, so we are just going to subtract our significant digits since it's a subtraction problem, and we get 7.04 when we do that. Scientific notation always has the times 10, and since my magnitude was already the same, I'm going to keep it the same. And I can notice 7 is between 1 and 10, so I do not need to convert this any further. It's already in proper scientific notation. So if we look at, I guess, our second number 2, or number 3, the Statue of Liberty is about 1.5108 times 10 to the 2nd feet tall from the base to the torch. The pedestal is 1.54 times 10 to the 2nd feet tall. How tall is the Statue of Liberty from the foundation of the pedestal to the top of the torch? So if I pay attention here, I'm given a portion of the Statue of Liberty from the base of the torch, and then the height of the pedestal, and I want from the foundation of the pedestal all the way to the top. So I know I'm going to be adding these together. So I have 1.5108 times 10 to the 2nd plus 1.54 times 10 to the 2nd. And since my magnitudes are the same, I'm going to add my significant digits, and I get 3.0508, and since my magnitudes are the same, it'll be times 10 to the 2nd power. Looking at number 4, a bank starts the day with 2.93 times 10 to the 4th dollars in the vault. At the end of the day, the bank has 8.7 times 10 to the 4th dollars in the vault. How much more money is in the vault at the end of the day than there was in the morning? Okay, so here we're looking for a difference. So how much money is there at the end of the day than there was in the morning? So at the beginning of the day, we had 2.93 times 10 to the 4th, and then at the end of the day, we clearly had more. So I'm going to take my end of the day value, and I'm going to subtract my beginning of the day value to see how much was added throughout the day. So again, since my magnitudes are the same, I just need to subtract my significant digits and then times 10 to that same magnitude of 4. And again, it's in scientific notation, so I do not need to do anything additional to make it so. It's already in scientific notation. Okay, when we're given problems where we have different magnitudes, we have to take an additional step before we're able to actually add or subtract. So when you're given different magnitudes and you notice that the exponents are different, you first want to locate the smaller exponent between the two. And then you need to decide what value you need to add to make the magnitudes the same. So if I'm looking at my first example, I see my smaller magnitude is 32. And I want to decide how much do I need to add to 32 to get to 34? Well, I would need to add 2 to 32 to get 34. So since I have to add 2 to that magnitude to get it to be the same, I also need to then swing the decimal in my significant digit to the left that number of spaces. So since I need to add 2 to the exponent, I'm going to swing my decimal 2 places to the left in the significant digits. While this does take this out of scientific notation form, it's necessary to do that to be able to add or subtract in scientific notation. So once I do that, I am then able to add 0.0295 plus 5.25, which are my significant digits. So let's rewrite that here so we see it a little more clearly. Plus 5.25, and that's going to give us 5.2798 times 10 to the magnitude of 34, because again, that was the magnitude that we were working to become the same. Okay, if we look at my second example here, I can see I first need to locate my smaller exponent. My smaller exponent is 42. If I want to get 42 to equal 45, I need to add 3, which means I'm going to take my decimal in 5.5 and move it 3 places to the left, which then results in me needing to subtract 8.94 and 0.0055. And so when I do that, we get 8.9345 times 10 to the 45th power, since that was the magnitude that we were trying to get to be the same in the very beginning. Okay, looking at my second number 2, or my number 3, the approximate area of the Pacific Ocean is 6.4 times 10 to the 7th square miles. The approximate area of the Arctic Ocean is about 5.4 times 10 to the 6th square miles. Find the sum of the areas of the two oceans. Okay, it obviously says sum, so I'm going to be adding my two numbers together. So 6.4 times 10 to the 7th plus 5.4 times 10 to the 6th So I need to locate my smaller exponent, which is 6. And I know I need to add 1 to that to be equal to 7. So I'm going to swing my decimal 1 place to the left, which leaves me with the addition problem, 6.4 plus 0.54, which is going to give me the value 6.94. And then my powers of 10 stay the same, times 10 to the 7th, which was the magnitude that I was trying to match when I added 1 to 6. And then our last question here says the approximate area of the Pacific Ocean is 6.4 times 10 to the 7th square miles. The approximate area of the Arctic Ocean is about 5.4 times 10 to the 6th square miles. About how much larger is the area of the Pacific Ocean than the Arctic Ocean? So we're going to take the area of the Pacific Ocean and subtract the Arctic Ocean value from it. So setting my problem up very similarly to the last, however, this time I am subtracting those. So since it's so similar, I can remember that I had to add 1 to 6 to make it equal 7. I had to swing my decimal 1 place to the left to keep it the same. So then we have 6.4 minus 0.54, which gives me 5.86, and then times 10 to the 7th. And that's how much larger. Be aware that I'm not asking how many times larger. I'm only just asking how much larger is the area of the Pacific Ocean. All right, go ahead and try your practice. See how you do.